Okay, let's get started. Sorry for the glitch from the projector. Somehow the screen isn't going to work with all the adapters that I used. I just checked the registration website and also the waiting list. I think now we already have about 8 or 7 slots opened up. So people will be gradually rolled in. And I expect at the end of the day, in 2 weeks, probably we will stabilize at 75. So hopefully everybody will be formally enrolled. If that still does not happen, we'll see. I will plead the official to make sure that no fire security violation code is, is going to happen. I'm going to get to register somehow. Okay. So, as I said last time, the summary of your reading is still physically in a hard copy at the beginning of the class. This is both to make sure that you read the material carefully, but also to encourage you to attend the class on time. Also, the reading, forgive us, the TAs and myself, that the reading material isn't 100% compatible with what I'm teaching in the class as of now, because there are some kind of delay and mismatching in the planning. But everything will go synchronized, after a few classes. So, for example, today what you submitted is the stuff I'm going to teach next lecture. But it's good. Nothing is wasted. Okay. So I want to make sure we have a scriber today. Who is scribing today? That's great. I appreciate it. 1 or 2. Okay, that's good. In fact, the earlier you do it, the easier. Later lectures will be only harder. You will actually see my overview of the plan of the class. And then for those of you who are still on the waiting list, your email address is not automatically included in our mailing list. So if you want to be informed about any announcements, please email the TAs and myself to get yourself included in the mailing list. Okay, so that's the only announcements that I want to make. Anything I missed? Any other logistic issues that I didn't cover? All right. So let me actually go with a very quick kind of overview of what's going to happen in the rest of the semester. Okay, spring semester is usually longer than the fall. Therefore, there are more lectures. I don't know whether you take it a good thing or not good thing, but for me, I need to do more work, but also I had the opportunity to teach more stuff, which is very nice. So the whole class will be roughly divided into 2 parts. Okay, and usually the pinnacle time point is the midterm time, and we don't have midterm, so sometime around the spring break, you will see a transition. So the first half will be the foundational material for graph models. That's pretty much the stuff you'll find actually in both Daphne and Neil Freeman's book and also Michael Jordan's book, which was written like more than about 10 years ago. That's the classical material that I want you to master. And that usually kind of occupies the entire kind of course of graphic models. But this field is evolving so rapidly. There are a lot of new stuff coming out. Therefore, starting a few years ago, I decided to gradually roll in like new stuff, which is happening right now in the research community. So here are some of the fancy topics that we're going to discuss. We're going to talk about some new techniques of approximate inference algorithm. In particular, starting last year, a lot of things are happening in distributed fashion of doing approximate inference, and we're going to talk about that. And then there are this new way of dealing with latent variable models, which is known as either a non-trigonometric or a spectrum approach to graphic models, which allow you to somehow circumvent certain local minimum problems that is plugging the graphical model inference research. And then there are another type of graphic model known as the so-called infinite graphic models, where you can somehow get yourself away from pre-specifying the number of clusters, the number of features you have to use, and so on, okay, using some alternative approach. These are very pragmatic, but it's very fancy, and interesting to investigate. Then a new topic that is also very popular and hot these days in the community is known as structured sparsity, how to learn sparse X. X being everything, graphical models, regressions, and other estimator, and so on. So how to enforce such sparsity in graphical models. And then if we have time, we may also study some alternative approaches of even dealing with the graphical model domain entirely. Right? Maybe moving away from the likelihood or probabilistic framework and using other principles to design loss functions, such as a maximum margin loss, in which you can now find a combination or integration of graphical model with a totally different community known as support vector machine, how these two things go together. Right? And if we have more time, we can go even further and investigate more integration, like how graphical models and Bayesian approaches integrate with non-parametric Bayesian, integrate with SVM. Everything could come together. We can even bring in kernel and spectrum methods all into this place. So at the end of the day, I hope what you get back home is that the graphical model is a very dynamically evolving domain, and a lot of things is actually happening, and there are a lot of opportunity to do new research. And the way I'm going to lecture the whole thing is going to be more insight-driven than math-driven. In fact, we could prove theorem all the time in the class. Okay, all these materials are very mathematical, and they do require a fairly amount of sophisticated mathematical skill, which I'd rather push it back to your home reading and self-taught, self-paced kind of education, because you may or may not enjoy that, and you may choose to maybe do that at different level of sophistication. And I'm not going to enforce a standard in the class. In the class, I'm going to focus more on the insight behind all these math equations, all these proofs, instead of boring you with writing lines of equations. That's why actually I'm not going to use the blackboard. I'm going to use PowerPoint slides. But inevitably, I need to use my pen to write some equations, if you forgive me, to explain some of the stuff I cannot explain in English. Okay? All right, so with that, let's start the first kind of encounter of the real technical materials in the graphical model. Let's begin with this old question about how to parameterize a multivariate distribution, right? And we learned that this is not a good thing to do if we just use a tabular distribution. And so what's the alternative? Well, we said last time already, there is a way for you to break this into a so-called factored representation, meaning that it's going to be expressed as a product of pieces. Well, in fact, without using any graph, you can already have a product of pieces. So this is the very well-known chain rule in probability. Now you can basically decompose any joint distribution into a sequence of multiplications of a conditional distribution. The first one being the first variable due to certain ordering, the second one being the second conditioning on the first, and the last one will be the last conditioning on everything before that, right? Do we gain any simplification from this decomposition? Any quick answer? Well, the truth is that the fact is that if this decomposition is applying to any multivariate distribution for 8 random variables, then we don't really save anything, because there is this fair life that if you don't lose anything, then you don't gain anything, right? So you will pay equal cost, and you can figure out yourself where the costs come from, in an alternative way. So you don't actually gain any representational cost. The other extreme is to make some assumptions. Okay, for example, I can basically make an assumption that maybe this guy, which is a conditional distribution of one random variable versus everything else, somehow we set them equal to P of that variable itself, meaning that the conditional distribution is equal to the marginal distribution. Then we can arrive at this distribution, okay, which is a product of 8 marginals. Okay, so what do we save in this case? Any benefit by doing this? Certainly there is a benefit, right? You get a lot of simplification in at least estimating parameters, because now you need to have 8 components in this product. Each component needs only one number to parameterize, right? You have a big saving. What do you lose? So in here, the statistical interpretation of this product is that every random variable is marginally independent of everything else. You have a lot of independence. Basically, everything is independent. Therefore, what if two variables are dependent? Then can this distribution represent that? You don't, right? So that's basically the first kind of insight that I want to deliver to you. Here I use a graph. This one corresponds to this graph, basically. There's no edge whatsoever between every random variable. And what does this one correspond to? If you view the whole thing as a graphical representation. Is that? A clique, yeah. Everything is interconnected, right? Then graphical model is about doing something in the middle. We draw a graph, like this, like you see last time, and it is a graph that is reflecting some kind of legitimate, pre-informed, causal or generative or correlation structures among random variables, but not, about all possible independence that could happen, okay? And therefore, graphic model is for you to, trade off between the richness in representation and the economy in representation cost, and get somewhere in the middle that pay the right amount of cost to get back the right amount of representational power, okay? And maybe it's also interesting to ask, say we have 3 different families of distribution. Say, let's say a distribution like this, okay, like this one, is we call it maybe a family of full graphs, okay? And we also have another family of distribution which is defined on a graph like this, which is a limited graph. And we also have a family of distributions which is defined on complete independence assumptions. Can you give me a set relationship between these 3 families? Set relationship means that which includes which one's bigger, and so on. That's an insight I want you to try to get adapted to. Okay, there is this hidden capacity, and there is this apparent kind of representational power. I want you to actually gain an insight about these dependencies and relationships. Which one is the biggest set in this case? Another way to ask is that if I come up with a distribution like this, can this distribution also represent this fact? Yes. Can we? Yes. We can, right? We can just play some trick in parameterizing it to set number in a certain way. Therefore, a special case of that is this one, right? And this one is right in the middle. So we should have something like this, okay? So now let's actually be more specific about quantifying this set. All right, so again, 2 graphical models type, and we're going to focus on the first in this lecture. And I talked about some notation, conventions already, and let me just reiterate a little bit. So we're going to deal with variables, values, and indices all the time in this class. And let's hopefully agree upon a particular convention, although I may myself violate, but you can remind me if I do. Okay, so we have random variables, which is just a Roman character. And they have sub and sup indices. Okay, and you know what they correspond to already. And sometimes, for various reasons, I may put indices like this. Okay, and because putting something here may be inconvenient or may be confusing with the power representation and stuff like that. And we also need to deal with the so-called random vectors, which is a list of such random variables. And sometimes we will use this, okay, to put to the error on a vector on top of that, okay, and this basically corresponds to something like that, okay. And in certain cases, we may actually have a matrix of random variables. In that case, I will use a bold-faced character to represent that, which is basically a set of such random vectors. Okay? And then I reserve the Greek characters to represent parameters. In fact, if you are a true Bayesian, there is no difference between parameter and a variable because everything is a variable. But again, they somehow play a little bit different roles, okay, in the graphic model literature. Parameters are to be shared across all the data you observed, and it is intrinsic to the model. And the variables sometimes are bounded with their affiliated data observations and so on. And we will be more explicit when we see more models. But in this case, very often I will use alpha, beta, and gamma to denote the parameters. Okay? Parameters, for example, is the probability of an event happening and so on and so forth. And also, I may have parameter vectors and so on. So the convention will be the same as this. Okay? Just to stick with that. And then let's talk about how to start with a representation. I'm going to motivate the problem, use a running example that I'm going to talk about now. And this running example will be actually revisit multiple times throughout the first half of the semester. Okay, it is based on a modeling challenge that you guys may or may not had experience with. Have you guys been to a casino ever? Las Vegas or Atlantic City, Macau, or Monte Carlo, these places? I've been to all these places other than Macau, but I wrote a few chapters of my thesis actually in Las Vegas, just because my wife really wanted a vacation after my 5 years graduate study. So here is one critical question we want to ask, right? When we were in a casino like this. Say you are facing a dealer like him, and you are going to play a game with him, which is described here. And very simple game. You guys, each roll a die like this. Each have a die and roll that. And who gets more points will get the money. Will collect the money from both people. Okay, very simple game. But suppose that after some play, like after maybe this play, you saw something strange. You become suspicious, right? There are, too many 6, and usually too many 6 other than other numbers. And you suspect, am I, basically fooled by the player, by the dealer, okay? And the way you can be fooled might be that there are 2 dice. This guy may hold, a particular die where 6 will occur 50% of the time, and all the other phases will occur, 10% of the time. And you, unfortunately, are given this fair die. Okay? So, and we are statisticians, computer scientists, we're very smart, so we want to really ask some question. First of all, very high-level question that anybody could ask, but then we're going to turn it into math quiz, right? So the first question will be, I see this sequence, and I'm suspicious. I now want to, and I have my hypothesis that maybe there are different dice and so on. I want to ask, what is the likelihood this sequence will be happening if I'm holding my hypothesis, right? How likely I'm going to be cheated? And so that's one question. The other question is a question known as decoding, which is, suppose I already believe there is a play there, and there is a conspiracy there, and I'm going to figure out how I'm actually fooled, right? So I'm going to ask, out of each of these particular outcome, what dice the dealer is using to get the number that I see. Okay, so that's the decoding question. And the third one, of course, is even a more challenging question. You want to outwin that dealer, and therefore you're going to really predict or estimate what is the frequency he's going to switch between dice and so on and so forth. So these are the 3 questions that we might be interested in. And I talked about this question in our machine learning class as well, if you were there. And then I'm going to now turn them into a graphic model problem. And let's see how, what is the most kind of intuitive way of translating what I just talked about as a story into a math problem. So first of all, I need to pick random variables, to be, a modeler. So what are the variables that I ran into in the previous story? Variables means that something you observe or not observe, you experienced, but it is a stochastic value that you are not certain about. So we need to pick random variables first. Right. So now I'm talking about knowledge engineering. So you need to now engineer your knowledge first.
The outcome of the dice roll?
Cool. Let's call it what? X? How about, let's be fancy and talk about math. Outcome of the roll. And then what? And are there other variables? The choice of dice you use to generate the outcome. Yes, let's call it Y. Okay. And you play, I guess, more than one play, right? So we need to probably index that, right? So, okay, let's call it I. Maybe call this 1. And maybe we have another one, call it 2. And so on, right? Okay, so we finished with picking variables. And obviously, these two type of variables are different, right? One is observed, the other is hidden. So we want to graphically probably distinguish these two, right? So maybe let's shade the observed ones. Just shade it, okay? Now we're done with the variable. We need to somehow build our knowledge of the domain into the design of the model. And we call them like structure engineering, or picking the structures. Say either a causal structure or a generative structure or a coupling structure, you name it. So in our case, what is our structure? Well, obviously, this observation is to be generated by the choice, the die that you chose, right? So how about putting two errors like that, right? So that's a very obvious way. It is a generative model. What other structures you want to assume? That's actually the tricky part, which is relying a lot on your creativity, assumptions, and willingness to compromise. Because you want to build a model which is offering you insights, capturing your knowledge, but also not too complicated that it is as complicated as real life. If you don't do reduction from real life, you don't get anything, right? You basically, why don't you just use your brain to compute? Right? The reason to use a machine is to hopefully try some compromise. So let's imagine the following. If I play the first die, and I'm going to really, I'm the dealer. I want to really, play some trick with you. What is a possible strategy? Do I have a strategy to choose the second die, or do I don't have any strategy? Right, have a strategy. Okay. Let's maybe forget about what strategy to use. At least there is a strategy, meaning that the second choice will be dependent on the first choice. That already, allow us to put another error in here, okay? Basically, statistics can say that maybe the probability of making choices between dice depends on what I chose in the previous one, okay? If I wanted so much to win, then, I really want to stick to the loaded die. So if my previous die is not loaded, I need to switch to the loaded die. If my previous die is loaded, I need to stick to that. Right? So that basically is a pretty legitimate, greedy procedure. Yeah?
Would the choice of your second dice be dependent on the outcome of the first one?
Yes, you could. Yeah. So that's, again, what I mean by the compromise or the greediness you have to balance. Right? I could probably, but that's probably maybe too obvious because, you and me both see the outcome. If your second choice is depending on both sides see, it's more easy to be guessed out. At least now I'm conditioning on something that the other side didn't see, right? So it's making less obvious. But you could equally like a more sophisticated procedure to make them more kind of covered, right? More secretive. For example, this guy may depend on the one before that, or multiple ones before that. So we can make all these assumptions. So here, I suggest use this one for simplicity. And then we are going to reuse this strategy on and on like that. Right? So that's basically a possibility of model structure. And that reflects a generative procedure that I assume to be true. Okay, that's the second step. And then the third step, okay, we already have a graph. Look, this is a graph, right? We have arrows and nodes. And to make it into a model, what else do we need? We need to put on these multiplying components, the building blocks of local conditional probabilities. And can anybody tell me what are the building blocks I need? For each edge, I need to have a conditional distribution of the children node given the parents, right? So, for example, this one, I need to have a P of x1 given y1. I also need to have a P of y2 given y1, right? How about I also write down P of x2 given y2, and so on, and every transition probability. Right? So these are actually, I missed one thing. Can somebody remind me? Okay, right. I need to also have a thing to kick things start, right? Okay, so I can certainly put such a thing for every edge in here, which is doable, but I may be too lazy to learn all that. What if I just see each of the event only once? Then I couldn't really estimate the probability, right? So one additional compromise is say, okay, I'm going to reuse this strategy on every transition. Therefore, instead of writing down P of y2 given y1, I'm going to do P of yi given yi minus 1, and P of xi given yi. This I is going to be 1 up to t minus 1. Okay? So actually to t, no need to do. So that's basically another choice. And that basically finishes the design of a model. Okay, so that's basically how do you turn a knowledge engineering, you turn an empirical kind of guesswork into a formal probabilistic inference problem using graphic model based on a knowledge engineering procedure. Okay, so I'm going to now start exposing you the statistical insight behind this very intuitive exercise to convince you that this is not only a heuristic, okay, this is a principled way that guarantee some nice outcome and also guarantee some statistical consistency, meaning that the other guy do the same thing will get the same result. The other guy do something different will have some other predictable results, in other fashion. Okay, so this is a hidden. By the way, this model, what you just built, is called a hidden Markov model, and the reason is because you have a hidden sequence of states which are evolving in a Markovian fashion. So that's why it's called a hidden Markov model. And here I have more examples about how this model is actually used, okay, in real life. And once you have that, okay, we now all know how to actually at least answer one queries, right, which is the likelihood of the sequence you see. That basically translates to what is the likelihood of a parse, both the observed sequence and also the hidden choices of the dices. And then that amounts to multiplying all these little terms. Okay? All right. And maybe here it's time to already expose you one challenge that requires us to use graphic model. Because you may ask, okay, it is all interesting and fun. Are there other computational utility of a graphic model other than just knowledge engineering? Well, there is one. For example, here what you see is P of x and y, okay, which is the likelihood of all the variables that you see. And you can easily multiply every pieces that we used in the construction to arrive at this estimate. But is this the real number that you want to compute? Is this useful for you? Or do you actually, what you want is somehow a little bit different from this one? Well, remember in the previous slides, I showed you that when you are playing the thing with your dealer, you are not going to see the y's because he's never going to disclose that to you. You can only hope to compute the likelihood of what you see, which is the x only. Okay, that basically, even if you know the model, you know how he chose, but you don't actually know the realization of his choices, right? So what is really needed is this step, which is to compute the so-called marginal likelihood of the data. And you use a marginalization or summation to get rid of all the hidden states that could possibly happen. And this is a step that takes a long time, right? How long it will take to compute this if you do it naively. Okay, so get some sense about the computing complexity, okay, other than just the statistical insights. So here, we're basically summing over every possible labeling sequence. And every labeling sequence has T states. Every state had however many, two in our case, possible choices, right? So 2 to the power of T possible hidden sequences. I need to sum over all of that. So it is exponentially many terms of summations, very expensive. And of course, you can now ask fancier queries we are going to address later, and that will be even more expensive. The point is that you don't want to do this naively, okay? The purpose of using graphic model is to allow you make use of this graphical structure and invent a smart procedure that can reduce the exponential complexity into something polynomial, okay? To the point it can be very low order polynomial as well. You can actually even implement that in your small machines. Okay, that's kind of the precursor of the whole kind of setup. And now let's start with this discussion. So we're going to talk about Bayesian network, and this is an example of the Bayesian network. I don't know why it is called a Bayesian network, but that's the convention. We'd rather call it direct graphic models, because this one may suggest you to take side between the Bayesian and the frequentist, but in fact you don't have to. So it is a directed graph whose nodes represent random variables, and the edges are representing some influences between the random variables. And it serves the following two purposes. Okay, so first, it is a data structure that provides the skeleton for representing joint distribution in a factored way. Okay, in a factored way. For example, you can write the variables like this, x and y, and you may or may not put an edge in there, and they basically correspond to two different types of conditional independence assumptions, right? What is the conditional independence in here? Well, x independent of y, right? What is the independence assumption in here? It is an empty set, right? Okay. So suppose that let's not having this graph, and we only have these two sets. Say we have two variables, and they could be a distribution that is having this independence or having no independence. And let's write down such a distribution. What do you do, right? What you do probably is the following. I'm going to put x and y here and pi here, and I just list a small table, and I have a pi 1 here, pi 2 here. And you can put in numbers here, right? And some numbers will allow you to satisfy this, right? And many other numbers will probably be more compatible with this. Is that the easiest thing to do? You play with some numbers, right? So that's one way. Without a graph, specifying a distribution with conditional or unconditional independent assumption can be tricky. It's doable. It's very tricky. And actually, later on, I will show you more examples of how to do that. But now with a graphical guidance in here, which allow us to write down, p of x and y as it is, as p of x and p of y given x, or in this case, p of xy equals to p of x times p of y. We actually change the way we parameterize the problem a little bit. In particular, in this case, we don't need to parameterize the original table. We can only parameterize only this marginal probability and that marginal probability. And I guarantee you that no matter how you parameterize these two two marginal probabilities, you are going to get back a joint distribution that is respecting this independence. Okay, so that's basically a way of thinking about the function or utility of graphic model. It gives you an easy way of building distributions that reflects conditional independence or marginal independencies. Okay. All right. Why I don't say the other way around? You probably notice that I keep saying independence. I kind of avoid saying dependence, right? For example, could I say this graph suggests a distribution that in which y is dependent of x? Can I say that? I just said that this one ensures a distribution in which y is independent of x. But alternatively, I could have just said this one gets you a distribution where this one dependent of that. What's the subtle difference in here? Yes?
Data that makes them accidentally independent?
What's that?
You could have data that makes them coincidentally independent.
Yes, that's the point. So in here, basically, I could just craft a distribution that artificially make these two things independent just by putting the right numbers there. Therefore, if I follow this rule and build my distribution, I cannot always ensure I have dependence. Okay, but in here, regardless how you do it, you're going to make sure, you're going to guarantee that you will have independence there. Right? So this is a safer claiming here. Okay, and then we can view this graphic model as encoding maybe a genetic procedure. That's going to be happening in the future when we do sampling procedure or inference procedure, where you can now simulate data using the graph. You can simulate y or x first, and conditionally on the value, you just simulate y based on that conditional distribution. Okay, so that's kind of a rough highlight of a Bayesian network. And here I make a formal theorem, our first theorem in this course. We say that, given you a DAG, and the most general form of a distribution that is in here, consistent with the graph, okay, that factors according to the node given parents. Basically, this one is the most general form of distribution that is consistent with the graph. What do we mean by consistent? Meaning that it encodes the same amount of conditional independencies as the graph encodes. Okay? So this is the theoretical guarantee of using this factorization rule for writing down joint is the right thing to do for Bayesian network. And we're going to prove that in the next few slides. So that's why you have this. Okay, so before I show the proof, I'm going to first give a few more words on how we're going to use this definition or this theorem, okay, to build distribution. You already see example. Now let's make it more explicit. So specifying a direct graphic model obviously contain two components, right? One is the so-called qualitative specification, which is roughly translated to knowledge engineering, and the other is a more quantitative specification. So qualitative one means you need to qualitatively specify the dependency structure, okay, or conditional independent structure in the graph. And then you put the table there, or put continuous value there as well, if needed, to make them a joint distribution. So now let's visit how each of these pieces is justified and how that should happen. So qualitative specification, in my opinion, this is the most fun part of good graphic model because you don't pay any cost. You can write anything you want and make a very fancy design of the model. And this is actually, in fact, in my opinion, the main purpose or the function of graphical models. Okay, you can basically, encode prior knowledges of causal relationship, of modular relationship. You can basically interview an expert and let him tell you a story, such as the biological pathway network we just discussed last class, and so forth. So it's a nice kind of way for you to interact with domain experts and empirical scientists. And recently, there is also a movement of learning such knowledge automatically from the data, okay, using the graphical model as a placeholder. And this is a very controversial practice. Myself do that, but in my heart, I still feel torn in convincing myself it is the right thing, but it happened anyway. The reason is because there are a lot of identifiability issue in the learning. to the point that when you learn two different graphs with different topology, they may give you the same number in terms of your loss function, such as likelihood. Therefore, intrinsically, learning the structure, the graphical knowledge from data is not necessarily guaranteed to be correct. Okay? And indeed, the graphic model is there for you to put your knowledge into the modeling process rather than getting knowledge out of the data. But that's just a personal opinion. I mean, even myself do this, and I'm going to tell you even how to do that in the best possible way that we can control in the later part of the class. So that's the easy part about qualitative specification. But now let's see what does this qualitative specification translate to statistically. That's actually the thing I want you to definitely remember. If you look at this graphical model, okay, you probably will notice that there are some regularity or some kind of basic building blocks in the topology. Okay? For example, you see this topology, which is called a common parent, in which you have one node there, and the two descendants. And that graph motif actually gives rise to a specific type of conditional independence called decoupling. Okay, it basically says that maybe I should P of A and C given B equals to P of A given B and P of C given B. Or in another word, I can write A conditionally independent of C given B. Okay, this is a graphical motif that leads to this statistical interpretation. And I have a story here telling you how that could be used in real life. The second one is called a cascade, which is a sequence of random variables connected in this way. And if you somehow observe something in the middle, then this is almost like a gate that is decoupling the predecessor from the descendants. So in this case, C is going to be independent of A given B. Okay, so these are two very trivial ones. In fact, we are going to, maybe if I had time, prove why this is hold. Okay, this independence is hold if we assume such a graphical motif and its way of defining distribution. The third one is a little contrived. It's very strange. It's called the V structure. It basically says that if you have these three random variables connected in this way, like two parents and a shared child, if you don't observe this guy C, then these two things are not dependent. But if you do observe this one, these two suddenly become dependent. Okay, this is a little bit counterintuitive way of defining conditional independence. So I feel necessary to give you maybe a little joke to explain this. Let's say, let me use this example. So you have this clock here, okay? It says 5:15. So let's define an event for that clock, this clock being precise or imprecise. Okay, so that's one event. Let's try another event. Maybe some traffic jam from my home to campus. That's another event. Okay, so these two events, do they actually dependent? Do they couple? They don't, right? These are completely two irrelevant things. However, let's define another event C, which is me being here on time to teach the class. Okay, so suppose that at 4:30 today, you see me, not present in the classroom. Okay, and so that you saw that event already, which makes it shaded. And then I ask you whether these two things are dependent or not. What do you conclude? Do they dependent? They are dependent in a strange way. For example, if you, for some reason, notice that the technician came and fixed this clock because they tell you this one is indeed not sharp, then probably your belief of there's a traffic jam from my home to here will decrease because maybe I just couldn't make myself here on time. Okay, you thought it's 4:30, maybe it's just 4 o'clock. It's not time yet, right? So that's the kind of strange way you can also, couple two completely irrelevant things due to a shared consequence they create. Okay, and this is also known as explain away. Basically, knowing one thing is going to explain the contribution of the other thing to a common event. Okay, so I claim these are the 3 foundational building blocks for creating a big, probabilistic independence graph, as I show here. And if you use them in a smart way, maybe even without realizing this statistical implication, you could build very interesting graphical models. Okay, that's why the language is very compact, but the concept is very, very rich. So here, not that you don't know how to prove, I'm going to give you a little proof of justifying this in a statistically rigorous sense, so that you actually know how such claim can be translated into a broader setup. And let's walk through the whole process to see how distribution is connected with a topology. So here I have a graphical model. Okay, and suppose that I follow the Bayes network definition of a joint distribution, then I basically can write the following, right? P of ABC equals to P of B times P of A given B and P of C given B, right? So that's basically a way of defining distribution based on Bayesian network. So that's one way. Then the second way, here, from this graph, I also have a conditional independence statement extracted, right? So here, A independent of C given B, right? And I call this a set of independence in my graph. Okay. Now I ask, suppose I'm going to follow the Bayesian network definition of distribution and try to write a distribution like this. And here, these are just placeholders of numbers of actual probability of different events. And I guarantee that however I write this, okay, however I put numbers in all these building blocks, I'm going to get a distribution with this conditional independence. That's basically the right question to ask. That basically ensures that you are going to, be correctly, unified between a rule of defined distribution and a rule of extracting conditional independencies to make sure they're equivalent. So I ask, regardless of how these 3 pieces are parameterized, okay, I'm going to prove that if or not, I'm going to have P of A, B, C defined in the previous way, having the same set of independence encoded in the graph. So that's basically a simple kind of a formal question I ask. It's kind of boring to go through this, but I think that's the simplest case I can show in a few minutes. And for bigger graph, you hopefully can convince yourself you don't need to ask this question anymore. Okay? So how do we prove that? Any suggestions?
Divide both sides by B.
What's that?
Divide both sides by P of B.
Okay. So basically, if I believe that this guy is true, then I basically need to have P of AC conditionally on B equal to P of A given B and P of C given B, right? If this is true, I get that. Then I can see from here, I'm going to copy that distribution, okay, P of ABC, and I still write down this equals to P of A, B, C divided by B, right? That's basically the very principled, axiomatic definition. And I'm going to copy this guy to here. Okay, and these two things cancel, I get what you stated, right? So even though it's very trivial, you can see that from here to here and from here to here, I use two completely independent reasoning, and they actually show to be equivalent in the end. That's why I say a graphical specification and a rule-based factor specification leads to an equivalent distribution. Okay, and that's actually giving you the freedom, and down the road, you can start actually building a graphical model based on just the graph topology and this rule without worry they violate any statistical kind of irregularities and mistakes and stuff like that. All right, any questions? So here I'm going to now start investigating the conditional independence a little bit in depth, maybe just only in this and next lecture, and so that you can build in your heart what statistically it means. So let's give some definitions. Okay, this is the first definition we need to know is the IMAP. IMAP actually is a vehicle for you to establish a connection between the graph and a distribution. So here we first define a distribution, okay, over X. And you probably should, be willing to assume that for any distribution, there must be a set of independencies associated with that, right? We may not know it, but there must be such a set. And then here, I'm also going to define a graph, okay? The graph, based on the rule I just stated, will define a set of conditional independencies. I call them a set I, okay? And I call this K, underlined I, to be a IMAP if the set of independencies due to the graph is a subset of the independencies of the set of independencies that I care about. Okay, then I call K to be an IMAP of a set I. Okay, and therefore, for every distribution in here, I can basically associate it with a graph which is an IMAP of the distribution, meaning that that graph is going to encode only independencies that is honored in this distribution. Okay? If this is true, then G is an IMAP of P. Okay? So now you can connect a graph with a distribution. And there are some trivial facts about the IMAP, right? Let's see. So why we actually need a IMAP to characterize the distribution? Well, because IMAP can be visually perceived. You can actually see that, and actually you can also run some algorithmic procedures. If I tell you in a second, to actually explicitly tease out all these conditional independencies. But if I give you a joint distribution as a table or something, you really cannot get it more explicit. So we need to make sure that the IMAP is tightly and correctly defined. And here are some examples that I want to repeat my previous statement to qualify what is a IMAP. So for example, here I have 3 graphical models, okay? And can anybody give me the I set of these 3 graphs? We did this before, but let's just review that a little bit. What is the I set of this?
X equals Y.
Yeah. Second one? Empty. Okay. Okay. So now I'm going to ask, I have a distribution, P of X and Y. Okay. And what is among these 3 different graphs, suppose I don't make any assumption on this, what is most likely to be the IMAP of this P among these 3 graphs? Any questions? Any answer? The last two are possibly are the IMAP, are guaranteed to be an IMAP of the distribution. Why the first one isn't?
Because it makes illusion.
Yeah, I kind of gave you an example already. So look at this one. This one, basically, here, the way to parameterize this two-parameter distribution can be arbitrary. You can put a lot of number here. But here, I just give you two options, two numbers. This is a number. This is a set of number. What's strange about this set of number? Anybody detect that? It kind of corresponds to y0 equals to maybe a what? 0.4, and y equal to 0.2, and this x1 equals 0.6, and something like that, right? Then, if you are willing to put the marginal distribution of x equal to this one, and the marginal distribution of y equal to this one, then suddenly x and y are independent of each other, right? So there is a hidden independence in this joint distribution, which is not, basically present in here, right? But on the other hand, if you don't do that, then there are dependencies in here, right? So if you use this as a IMAP, it basically insists that there must be this, but not that. Therefore, it is, in an overstatement about the conditional independencies in this distribution. Okay, so that's kind of an implication. You can basically create independencies or not, depending on how you parameterize that. That's why independence is a very safe and conservative statement about the graph properties. Yes? Yeah.
Can I go back to the last slide? The definition of the IK, like the graph object here, no, the last one. Oh yeah, here. So it says that if the IK is consistent in the I, so how it decides which I we are looking at?
The I is basically your choice of interest. It depends on your study object. For example, here I define the I to be the I of that. I is basically your reference point, the set of independencies that you want to characterize. Yeah. Right here, I'm working on a distribution, therefore I care about a set of independence of this distribution. Okay, so it is not a fixed thing. It depends on your problem. And then you are basically trying to translate this problem into a graph. And I claim that that IMAP is the safest graph that you should translate to, which only consider the independency that is already in this distribution, right? Okay, so now let's be a little more specific about the kind of independencies, okay? There are different ways of saying in English, the independencies, in a graph. And here I gave you one example, which is characterizing only the so-called local Markov assumptions or local Markov properties. It says that give you a graph, you just go every node, and you will have the following conditional independence property guaranteed to be realized, which is every x of I is going to be independent of their non-descendants given their parents. Okay, I just say it here. Go home and stare at your graph at these three motifs and convince yourself that they are true. Okay, given the parents, their non-descendant is going to be independent of themselves. This is not quite satisfying if you do have children. If the node does have children, then it's not included in here. Of course, you can run the children's children and take the children as the parents, but that's a little bit inconvenient. So people invent a more complete kind of characterization known as deseparation. Okay, deseparation again comes with a very interesting story. So it's basically defined on now three sets, arbitrary three sets in the graphical model, x, y, and z. It says the following. The two sets x and y, which are of your interest, is they are deseparated, deseparation actually is equivalent to conditionally independent. So they are deseparated given Z if they are separated in the more or less ancestral graph. Okay, very, very kind of indirect statement. You are using a different the property of a different graph to characterize the property of another graph. So here is a graphical illustration. So we ask whether X and the Y are deseparated. The truth is that you cannot see that from this graph. Okay, there is a thing here, and we need to first go to the so-called ancestral graph, in which their kind of children or child of any node of interest is going to be removed. Okay, so here Y and Z both have a child. The child get removed. So that gives you an ancestral graph. Then the ancestral graph is claimed to be unmoralized if the child, the parents of any child is not married yet. Okay, and they are not married yet. So for example, in here, we have a Z which has a pair of parents, but they are not married in the sense that there is no connection between the parents. Therefore, we need to make a connection between them to marry them, to make the whole thing moralized. Okay, so that's the moralized ancestral graph. I don't know who invented the term, but I think sometimes to sell a nice idea, you need to have a fancy story to tell. I guess that's what happened. So at the end of the day, you translate this original graph into something very strange called the moral ancestral graph. But there are some good utility here. Look at here. Suddenly, there is a path from X to Y. Okay, and the Z cannot now block X from Y. And therefore, X and the Y are not conditionally independent given Z. Okay, so that's basically how to define deseparation, which is a graphical operation. You need to resort to a different graph. So, okay, remember that rule. Kind of contrived, but it is the authentic, most kind of complete definition of conditional independence that applies to all parts in the graph. Well, it is a little bit inconvenient, right? Yeah, questions over there.
Yes, so what exactly do we remove to get the ancestral graph?
We remove any child resultant from the node of interest. For example, here you are talking about X, Y, Z. Their child need to be removed. Yeah.
My question is, should the child only be unobserved, or it can be?
No, it should be just removed. Yeah. Here we're not talking about observe or unobserved. We're talking about graph manipulation only. Yeah. But still, it's kind of funny and inconvenient because you are using another graph to work on your original graph. So people invent another procedure called the active trail algorithm, which basically defines on the original graph a few trails. Okay, there is a thing called causal trail. Okay, and there is another thing called the evidence trail, and so on. And then they basically also have another state, which is whether the trail is active or not. Okay, the state of activation depends on whether some elements in the trail is observed or not. So in this case, this trail is activated if this guy in the middle is not observed. Okay, activated, I can see you can go through without block. And the evidence trail, same thing. Something in the middle is not observed, then this whole thing is activated. Otherwise, it is not active. Common cause is another trail. No, common cause. If the common parent is not observed, then the trail is active. Okay? And then this last one is the strange one I just mentioned about this V structure, which has a common consequence. This is a little bit strange. They are only active if this guy is observed. Okay, otherwise it is not. And but to make the story even more funny, you have actually also this. And if this guy is observed, then the trail is still active. You can pretty much go like this. Okay? So now we basically have a different statement about the deseparation. If there are 3 nodes, or 3 sets of nodes in the graph of the graphical model, and if there is an active trail between the 2 sets of interests, then they are not conditionally independent. Okay? Isn't that a little bit simpler? Right? You don't have to use a new graph. The original graph suffices to give you all the answer you want. Okay? So that's the so-called active trail algorithm. And just to make it more fun, someone even had this so-called the baseball algorithm, which is just a almost game-ish kind of realization of the active trail. You are going to send the ball from here to the rest of the graph and see whether the ball will be reaching the other end. And obviously, if the trail is active, the ball can go through. And if the trail is not active, the ball will bounce back. And then you are going to basically detect whether any pair of sets of variables in the graph is conditionally independent given the third set using this approach. At the end of the day, once you run this algorithm, on the whole graph, you are going to get a set like this, S of j, which includes all the conditional independence statements or propositions on the graph, which never people do, in fact, because it is too tedious to get all of them out. Maybe for fun, you can go home and do this. I have 4 nodes, and you can run your active trail or baseball algorithm to get all the conditional independent clauses from this graph. I think there are 5 or 6 something, but I welcome you to play with that. Okay. So why we actually need all this exercise? Do people really care about getting all the conditional independencies out of a graphical model? Right? That's actually a good question to ask. I don't know. I mean, my personal opinion is that it is not necessary. You don't probably need to care about all this. This is really a vehicle for people to be able to prove that structure-defined distribution is going to be equivalent to mathematically defined distribution when you don't use structure. Okay, and the equivalence is built on the shared set of conditional independencies from this 2 kind of a vehicle. Okay, but sometimes if you are a logician, if you really want to build interesting dependency queries, or if you are a biologist, you really worry about whether a gene is influencing the other gene and so on and so forth, and want to build a treatment out of the inference, you may actually care about this. Then that becomes a useful tool. Okay. Okay. Any questions so far? I have 10 minutes left. I'm going to rush now, speed up the pace before getting questions. 3 slides before. Wow. Oh, there are differences. I mean, they are graphically different already. Right. They look the same, but once I name all these variables, this is x causing the other one, the distribution will be different. The distribution is different. Maybe this is a discrete distribution, this is a continuous one, and now continuous conditioned on discrete, and you have here discrete conditioned on continuous. They are mathematically different. They may be symbolically similar. Right. Okay, so I want to wrap up the presentation of the independencies by this statement. Okay, this is a very important equivalence theorem that you can get a distribution D1 family from those satisfying this, which is rather tedious to satisfy. You need to basically test all the numbers and check whether each of the statement is satisfied. Or you can use this very simple factorization rule to synthesize a big distribution, and at the end of the day, they are equivalent. Therefore, what you do is to get a graph, use this, and you get everything you have. Okay? All right. So the other part is rather trivial. You have the graph, and it is now statistically proven to be legitimate and consistent, and the put numbers amounts to putting all these local conditional distributions wherever necessary, like the node, the margin node, the condition node. It could be a tabular form like this. It could be also a continuous one like this, right? If you have continuous one, maybe the first one is a Gaussian, and the third one, how does one Gaussian depend on two other Gaussians? Well, many different ways. The way I choose is to use the first two Gaussian to define a mean for the third Gaussian. These are basically your own choice. Okay, you can do addition. You can also do point-wise multiplication and many other things you can do. Right. All right. So that's the summation, the summary of the Bayesian semantics. You have the conditional independence, which imply factorization, and then you have the factorization conversely imply conditional independences. Now, before I go away from this topic, it's just intellectually interesting to now push a little bit deeper to ask, does these two really, are they really equivalent? Okay, this is actually something I try to convince you to be equivalent from a very high-level qualitative statement. But the real kind of mathematical way to say that is the following. You have a soundness kind of a statement which says that if a distribution factorizes, then you have this, okay? And then if you have a distribution, for any distribution that factorizes according to graph, and then you need to have basically, the reverse direction where all the independencies in the P is going to be captured in the graph. Right? So these two ways of all independencies in the graph should be in the P, and all the independence in the P should be in the graph. And my question is that, does this two direction all go through? This is a very, very subtle question. Okay, I don't really have much time to go into detail, but I can tell you that it is a little bit tricky to say for sure. This direction is say for sure. Okay. We actually showed enough examples previously already. All the independence in the graph that you can imagine will be realized in the distribution that you parameterized based on factorization. But in here, if you have some independencies in the distribution, are they always in the graph? That's actually the question. Anybody want to give me a guesswork and give me a counter example of a true example? Say I have a distribution, GP, which I actually constructed from the factorization. I did all the multiplication of pieces, and they will have the set of independencies. Are all the possible independencies in such a P going to be reflected in the original graph?
You could have a complete graph, which would be the final.
You didn't answer my question. If I start from a complete graph, then my P is going to be constructed that way as well, right? So I'm starting from a graph. So my graph gets you to the P, and now I'm asking the P will get you an I of P. Is I of P also in I of the graph? Maybe I should make it a little bit more tricky, more or less tricky. G to P of G, and to i's of P of G. And now, do I still have this kind of a very loopy story? But I want to make sure that you really understand how hard it is to manipulate distributions if you're not careful enough. Any comments? Just guess.
For example, in the case where you just have two nodes and you have one node leading into the other.
Yeah.
That's basically all distributions can factorize like that.
Mm-hmm.
But you can have, so all distributions have that property that they factorize over this graph.
Mm-hmm.
But a specific distribution can also have independencies of both x and y. But that would not be separated by that
You're getting there. That's basically, resorting to the little, special case I just talked about. What if I engineer the number to create some independencies purely from the number, okay, which may not be actually in the graph. And I have some reasoning here, which, do I have a graph? Okay, not here. But anyway, you can see this example, okay? So, as you said, I don't even need to do hard work. Suppose that I have this graph from A to B, and I just put these two conditional, A, B, to be equivalent, regardless of the state of A. Then it basically says that B is independent of A, right? But that's not actually in the original graph. Therefore, it is an extra independence. But that said, here is a safer theorem, which is a little bit amusing to state. I say, now let G be a Bayesian network, and if X and Y are not de-separated given the Z, then the X and Y are dependent in some distributions that factorize over graph, not all. So what's left out? It is this kind of thing. Okay, these are called the zero mean or zero measure distribution, where basically we are, artificially, wipe out, a chunk of possible configurations to give them zero probability, and we shouldn't allow that. We basically say every event has a non-zero happening. Once you parameterize that, then this will be honored. Okay. All right. I think that's all I want to say today. I will have 1 minute to go back to our hidden Markov story. Okay. So now, with everything together, you should be able to, be assured that you can use the graph to encode your knowledge, and then put, at a specific edge or, a specific subgraph, a local condition distribution satisfying your needs and your data, such as a discrete distribution for your, dice tossing, or a continuous distribution for your other continuous observations, such as speech signals and stuff like that, and then construct a model like this without worrying about certain strange kind of configuration being missed from your construction of the model. And then after that, we're going to actually have a very kind of safe vehicle for us to do the next step, inference and learning of graphical models. Okay. So with that, I close today with the following summary. You want to actually take home these basic messages, okay, which could be the summary of your submitted, the node you submit today. And that's basically something I want to see in your later summaries. Maybe slightly more than that, but to make sure that you get the essence out of your reading. All right, we're right on time, and now there's no class for next Monday, and I'm going to see you next Wednesday.